Hello, welcome to my Physics 2212 Lab 1 Charged Tape. The purpose of this lab is to determine the charge of a tape by making one tape float over another. The two main physics principles used are the electric field produced by a charge and the force that the field exerts on another charge. A brief preview of the lab is that the charge was measured to be -7.83 nanocoulombs. Some of the assumptions made is that all charge is located in the center of each tape, that both tapes have the same charge, there is no air resistance, and the tape's charges remain constant. As we can see in the diagrams, the tape is originally hanging, but after introducing another charged tape below it, it starts to float. The system consists of the charged tapes, while the surroundings are everything else, including Earth. For the initial conditions, the length of the tape is 25 centimeters and its mass is 0.25 grams. After conducting the experiment, we measured that the tape begins to float when the separation distance is 1.5 centimeters, as seen in the image. Because the tape is floating in a fixed position, its net force must be zero. Therefore, the force of gravity is opposite in direction and equal in magnitude to the electric force. Solving for the charge in this equation gives us a value of plus or minus 2r times the square root of pi epsilon 0 mg. But since we know the tape attracts with a positively charged pen, its charge must be negative. Plugging in all of the values into the equation gives a charge of approximately -7.83 nanocoulombs. To determine the number of electrons transferred, we divide this value by the charge of an electron, which gives a value of approximately 4.89 times 10 to the 10. To calculate the electrons transferred per atom, we searched the material that the tape is made of and calculated its molar mass. With this information, we determined that the tape has approximately 1.75 times 10 to the 21 atoms. Then we divide this number by the amount of transferred electrons, which gives 3.58 times 10 to the 10 atoms per released electron. In this slide, I explain how I programmed the computational model. In the top left, I define various constants, such as Coulomb's constant, acceleration due to gravity, the tape's length, and its weight force. In the bottom left, I wrote a utility function to plot charges on the x-axis and forces on the y-axis using logarithmic scales. In the right, I define the various functions. The electric field function calculates the electric field produced by the source charge at the observation position. The estimate charge exp function determines the net force on the hanging tape by trying out various values for the charges of the tape using an exponential step. Here are the results of my computational model. On the left graph, I charge values between 10 to the negative 20 and 10 to the negative 5 coulombs. As we can see, approximately at 10 to the negative 9 coulombs, the net force is almost zero. The graph on the right is like the graph on the left, but uses a much more limited charge range, approximately 10 to the negative 9 and 10 to the negative 7. As we can see, the net force is almost zero when the charge is approximately 8 times 10 to the negative 9 coulombs. Some of the assumptions made by the computational model are that it treats the charge spread along the tape as a point charge in the center of the tape. It also assumes both tapes have the same charge, which may not necessarily be the case. A similarity between the experiment and the computational model is that they both predicted a charge of approximately 8 nanocoulombs. This is likely because they both use Coulomb's law as the underlying physics principle. The slight difference in the results could be due to the iterative approach of the computational model, which contrasts the mathematical approach of the experiment. Some sources of error lie in the fact that some of the simplifying assumptions are not correct. For instance, the charge is not concentrated in the center of the tape. The tapes could also have different charges. Furthermore, the support on the hanging tape exerts a force on it, but in the experiment we ignore this force. Also, some of the charge is dissipated to the surroundings and the measurements may have inaccuracies. The first question is, what if electrons and protons switched charge sign? The answer is that nothing would happen because objects that repel would still repel because they would still have the same charge, and objects that attract would still attract because they would still have opposite charge. The second question is, why is it important to handle tapes as little as possible? and this is because while we are in contact with the tapes, some of the excess charge in the tape is transferred to our hands, which reduces the charge of the tape.